The dot product is it's the basic tool that we're going to use to build all kinds of similarity functions in this course. So when we talk about the similarity of a query Q to a document D, pretty much all the time it's going to have this form. It's going to have the form of a dot product. So we're summing up over all the words W in our vocabulary, and we have QW, that's the weight of the word W in the query. GW is the weight of the word W in the document. If you don't like the word weight, think of it as the coordinate, right? That's how GW is how far document D is on the coordinate that corresponds to the word W. Now, so that's the general form of the similarity function, but what you should immediately see is there is actually a lot of freedom in the way we set QW and DW. And it turns out that depending on how you set those numbers, you get similarity functions that could be either pretty crappy or similarity functions that are really, really good. So what we'll devote the rest of the lecture to is we'll talk about how to set those weights, particularly the DWs, in a way that leads to a really good similarity function. And the way we're going to do it is I'm going to talk through some basic observations of what you might want to have in a similarity function. What factors are important when you're building a similarity function? So the most important factor, obviously, is the presence or absence of words. If if I have the word aardvark and it occurs in the query and it occurs in the document, the very fact that it occurs both in the query and the document is the most important observation to make. So the simplest way you could set both Q and D is you could set them to binary. You could say, well, if the word is present in the document, then the value is going to be 1, and it doesn't matter how many times it's present or how long the document is. It's going to be 1 if it's present, 0 if it's not present. Same for the query. So, and we've already talked that when we do that, this means that our document is going to be a binary vector, and that's the same thing as a set. So when we measure dot product between two binary vectors, that's the same thing as just the set overlap, set intersection. So that's the way we usually write it out. And the name for this algorithm is usually the word overlap algorithm. It's also called coordination level matching, and there's a few other names. But you're basically looking at how many words are in common between the query and the document, not counting the repetitions. Now, why don't we count the repetitions? Repetitions are actually important. So if you think about the example that we had with our two little news stories, with the stars and single stars and double stars, the word stars, arguably the most important word in the stories, it occurred multiple times. Right? So it occurred 4 times in one story, twice in another story. So what you would want to do is you'd want to somehow reflect that frequency of occurrence. Say that if you have a word that occurs multiple times, maybe it's more important. So the simple way to do that is to just use the frequency or the number of times that the word occurs in a document as a value for DW, for the weight of the word in the document. So that frequency, it's usually called TF, term frequency. I'm going to write it as TFWD, so that's the term frequency of the word W in document D. So if we use TF for both the query and the document, then this is what our dot product is going to look like. Pretty straightforward, right? I'm just multiplying frequencies together. Now, this is all fine and dandy, but there's a bit of a problem with that. And the problem is, if I build a similarity function that looks like that, it will have a bias. It will have bias towards long documents. So let me give a specific example. Suppose I'm writing a search engine, and my search engine is, as its set of results, my search engine is going to return both very short documents, maybe tweets, and very long documents, Wikipedia articles. Now, a tweet is never going to have repetitions. There's just not enough space. You don't have enough characters to put the word stars there multiple times. You're lucky if you get it once. Okay. An encyclopedia article or a book, on the other hand, easily have lots and lots of repetitions. And what you could have is you could have a book about something completely unrelated, maybe a book about aardvarks. And once it will mention that aardvarks like to gaze at the stars. Right? So you have one occurrence of the word stars in the book. Now that occurrence, if I use the TF representation, will count as much as the single occurrence of the word stars in a tweet. Do you see how that's problematic? The word stars in aardvark, it really had nothing to do with the topic of the book, but you would rank them equally because of that. So that's not a good idea. So what you want to do is you want to somehow say really long pieces of text, they might contain words accidentally, right? The word occurrence might be tangential to the topic. It's not really what the book is about. It's just raised in some argument. So a simple way to compensate that is you could normalize those frequencies by the length of the text that we're working with, right? So we could say that for our weight dW, we're going to use the term frequency of the word W and D multiplied by the length of D. So I'm doing it for the document. Note that I didn't do it for the query. Why?
Because that's going to be specific anyways.
That's query is going to be specific anyways. Okay, that's one argument.
You get the importance as well. How important is the words in that?
So let me rephrase that question. If I normalized by the query length, what would change? Nothing. Right answer is nothing. Yes. So information retrieval is inherently an asymmetric problem. If I divide by the query length, yes, the numbers will change. The numbers for longer queries and for shorter queries, they will be different. But when you are retrieving, when you're doing the ranking, you have one query. You have one user, one query, and a lot of documents that you have to rank. What matters is how the documents get ranked. But the query is a constant. It doesn't change from document to document, right? That billion of documents that I have in my index, whether I divide by the length of Q or not, that length of Q is a constant across all documents. So does it matter if I have a bunch of retrieval scores that look like that? Does it matter if I divide them all by the same number? No. The numbers will change, but the ranking will not. The documents that ended up in ranks 1 through 10 using this formula are going to be the same ones that end up at ranks 1 through 10 if I divide by the query length. So now this is a really minor point, but it's the earliest symptom of a really big idea. And one big idea that we'll be using a lot in this course is rank invariance. Right? Rank invariance means you can take a formula and remove some component out of it or add some component to it, and it'll change the numbers, but it won't change the ranking. So, and it's used all over the place. It's an important concept. I'm just trying to raise it early, right? So the answer to that question is, yes, I could have. I could have divided by the query length, and it would have made no difference whatsoever. Makes a difference in the scores, but not in the ranking.